Diego will tell us something more about how to actually do the calculation of the free energy action. So feel free to stop him and if you have questions, if there is something that is not clear, stop, and if you want to look to the terminal, which quickly stop us and ask a question, because that's the best way. If you have some doubts, it's very likely that other of you also have the same doubt, so please stop us. The target here is not to show off ourselves that we know how to do these things, but for you to learn how to do so. It's very important that, if you have any question, do it during raise your hand and don't worry to interrupt, because that is the purpose. So with this, I give word to Diego.
Okay, I'm good. Oh, okay. I'm going to try to solve the problem that we had the other day and make it slower and kind of more easy for people to follow by typing directly the commands into the Python program instead of just reading them and I'm showing you as this. So you can execute Python code directly into Python just by typing Python with anything else, and then it opens you a prompt like this. I can open another screen here to show how it's just Python, and then it opens here with this to enter the commands in Python. So you can try that, and that way we can follow from copying and pasting from the documentation that you have. So in this case, we're going to follow this script. First, I'm going to explain that, well, first we need to make the first free energy minimization to do the before doing all the Hessian and that kind of thing to find this second order calculation. So first we just copy the import of the cell constructor and the SHA. First copy this. Okay, so let's copy this into here, and what's here? See, it's not I. Okay, so we'll put the I import, and that's we import the cell constructor. We import now the SHA. Control C and put. Also, I didn't put the first I. This is something that I have to fix. So right now we import the libraries for the SHA and all the things we need for the SHA. For this calculation, we are going to use a toy model to show that we can use any calculator. In this case, is you already think you have to have installed if you follow the instructions. This potential here, the Control C and copy here. And right now I copy with the import. I hope you all have this thing installed. If not, yes? You could follow from this, from the installation at the beginning. You should have the one for the here, the toy model installation. This is the one that we're going to use. It's a model that, well, as you can read here, mimic the physics of ferroelectric transmission in FSS superlattice. I hope you have all. So we can put it here, and we can follow the rest of the here. Okay. Next, okay, thank you. We can import the library for taking a look at the kind of crystal we have. That is this, the SPGlib, the library, and the visualization library from ASE. So we copy all this also for later. And of course the NumPy, the manprop-tip, and other libraries that we can use it later. Probably I could load it later also, but we have it here. Now we set the variables for our calculation. In this case, the temperature equals 0, and the number of configurations. So we're going to copy all this. Yeah, and the configuration. Equal, and the number of configuration, in this case 50, which is a low number, but we will make our calculation faster. We now need to load the dynamical matrix for the system. In this case, we're going to use these ones here that you should have. Technically, we need for loading the name of the files that we set here, and the number of irreducible Q points here, and set this is for the output, the frequencies. So that's how that is for the output. So we're going to copy this now, or we can copy it later. It's not a problem. Here is where is the calculator for this system, or the system for all this hands-on. So yes, here is the setup for this. I first need to set the FF calculator. Should be, it's easier than I thought. I thought that I was going to do it better this way, and I'm not doing it better. So basically what I'm doing is setting does not exist.
You need to copy the files.
The files first.
Yes.
Yes, so I'm going to exit here and enter in a place where I have all the files already done. So I could enter now in Python and copy everything again.
Maybe you can use the Jupyter notebook app so that you don't need to.
Yes, also, but I was trying to use this to make it so everybody can use it, even if they don't have that system installed. It's more clunky, but probably for people, because the other time some people, I noticed that some people don't know how to use the Python as is. So we can repeat everything that we have done until now. This import all the libraries. I forgot to put this. Okay. And setting everything. For some reason, I don't pick the first letter. So we're basically following the script. We load the dynamical matrix here. That's the first. Probably I should put it something to show what are we doing right now in more schematic way. But basically, the structure is always the same. We load the dynamical matrix that was previously calculated. We set the calculator, and from that, we run the minimization. So let's do that. Copy, paste. Now, it didn't get an error with the force, the calculator. And we can copy now this for the initialization of the dynamical matrix. What? Zoom. How to?
It's
Control plus. Okay. Yes, that's better. So right now, what we have done is just setting for the calculator. Right now, we are going to put the dynamical matrix into SSCHA with this command to create the object. So copy here. Then, because this has imaginary frequencies, we must make the force positive and make the symmetrization, the sum rule, or the calculation will give us an error. So copy and paste. And create this sample. At this setting, this dynamical matrix that we have just created, setting the temperature, setting the supercell. In this case, we load it from the dynamical matrix. So we copy this, paste, and done. We can now detect the space group with the library that we have loaded previously, this SPG-lib. This is only to show, to have we can look at what kind of structure is this. So this is not something to make the proper calculation, it's just to visualize that we begin with the FM-3M system, which is detected from this library, space group. And now we do set the minimizer, the SSCHA minimizer, in which this uses this assembly that we have created. In this case, we are not going to work with the root 4. to make things faster. We set the step as yesterday, 0. A quite big number to make it faster. The condition of the conjugate ratio, this is the standard, so we don't need to put it like this. We don't need to put. So, but you want, well, we can do it. To set a different value later. And here, we create the object to do the automatic relaxation, taking the minim that we have just created, using the calculator that we have the toy model, the number of configurations that we set previously, that was 50, and setting a maximum population of 50. That means that if the cycle of calculating after taking the new Gaussian distribution is more than 50, it stops automatically. So we can copy this here, and we have set the relax. And now that we have set the relax, we can do the relax. Or you can do the relax just Pascaling this relax here, relax. But first, as before, we're going to set the output to save some files here and tell the relax object to use that functions that we have defined. And now we just relax the system. Relax. And now it makes the relax. We have only, yes, because this is already relaxed. You press enter, it will take you longer in your computer. Right now, what we have here is obtaining the minimal force, the free energy. So we can save it into a file here. Detect again what kind of system we have, again with this library. We can see what that we are in the FM-3M. It's the same because in this case I taken the data already relaxed. You probably has different one or not. And we can also use the IS library to have a visualization of the atoms. We can take a look at the system here with the IS visualization. And with this, we set the free energy minimal. And as before, we can go outside, take another terminal, or get out of here. We can quit, exit. Here, and we can take a look at something that I don't have here. Upload data. I didn't save the frequencies here.
I think we didn't save the chart.
Ah, yes, they have 0.5, yes, dot 5 with a asterisk. Yes, I don't have it here. So I have to copy from another place. Or yes, we have in the previous the one. Oh, we should have it from the previous one.
You don't need to copy, you just run
Yes,
SSCHA.
from the previous one, I can use from the 01.
You just remove Python because you have installed it.
Yes, but the problem is that I don't have here the frequency saved. That this has in the part of the code here, we have set the output of the here the output to set to this file frequencies, and here in some place of the code we have to make the save of the output file frequencies here. So it should be saved here in the file. That's the name of this file. So probably I have already the code here. So if you follow that, we set here the name of the output and set the output to be written and the input output here, and then it should be we should have a frequencies output. That is not here. I don't know why. Oh, I see. I don't know what happened here because technically uh, when we did this calculus, we should put an output in final frequencies point dot dat. This is the output that we are sending, and file frequencies, and in input output within the file frequencies, and in the relax we're calling this function to save. And saving the final flags. So it should be here. I don't see it. I'm going to change the output to another to frequencies without insert. Please insert without this to get a new one. And try again. Okay, I don't know what happened here. Probably I'm doing something wrong. I'm going to copy the code. One, two. I'm sorry, I'm doing this mess.
You're not copying it,
I'm not copying. I'm doing CD. Just I see CP, CP.
you have them, I think.
Yes, I should have it. One. So now I have a clean with just the Python code and the dynamical matrix for the four fields. So right now, it should work and do the calculation and have an output with the new dynamical matrix. Here we have final, we have this other one, but I don't see. Okay, something is wrong here.
Never mind, go ahead. So you did the child minimization, right?
Yes. Because I set the name of the output here, and then the input output, I set it here with file frequencies. I can do it manually. Just use nano. We're going to put it here, the name of the output file that output, and right now it should make the calculation and put the output in output. I should have some output somewhere here.
Can you see the output of the Python?
Ah, yes, I mean, you mean this?
Yeah. You don't see anywhere.
Time report. Oh, it's failing to.
Yeah, it's not finished. It has some timer assembly.
So, what is failing here? I'm kind of lost. We have symmetries. We have population number 2. Which is not right. Time report. We have the ability on the stress. We have here the first.
Oh, it found imaginary frequency.
Yes, but we should have taken that out of with the
Remove the step. Yeah. So make it smaller the step. You have 0.5.
so the step is too big. Where do we set the step?
Below, below.
Below.
Yeah.
Yes, with after doing the
There.
here. So I'm going to put it lower. Maybe was that too big?
Yeah, let's see.
No.
This is good.
Yeah.
Yeah.
We are looking at all the problems that we.
the errors. Okay.
Uh,
No, can you scroll up just to see why it stops?
Yeah.
I can put the output to an and just read the output file. So here we are loading, this is the initial structure. We compute the configurations. First, disable properties. The first step. That's number of symmetries, harmonic.
What is the problem?
Uh,
One step. So
Yes.
so this problem. Yeah, the problem is that the meaningful factor is too big.
too big, yeah.
So you have to reduce it to 0.01.
So still too big.
No, the meaningful factor, which is not included in the
Yeah.
file.
Yeah.
So maybe it's good to set up the meaningful factor.
Minimum factor for the minim, yes. The contain minimum.
There you can put it maybe.
Meaningful. E.
Yeah.
Is,
Yeah.
no, it's again.
Mes ning full
Underscore.
factor equal to 0.01. So
Okay.
make it small enough.
Yeah, like that should go well.
And now we can of the output.
Yeah.
Okay. That was the problem. It was too big. I was trying to do a too fast calculation. And that means that the output should be in output. Yes, right now we have here output 5, output that with that, and here we have the free energy, the error, the gradient, the strato gradient, the convolute, everything is here.
So can you show again the out of the mean what is set up?
Yes. Here, after creating the object of the minimization, we set the different parameters for the minimization here, with this case with the step and the minimum factor here.
These two factors, remember, are one is the step
Step of the
gradient descent, and the other one is the factor that compares the error with the value, right? So the delta to my slice.
and with this consecute, we have the output, so we can plot the as we did before. Plot, where is the plot? SHA plot with the output that and frequencies, which is the name that we changed it. And we have here. Okay, we see that the free energy effectively goes down, the gradient goes to 0. We have only one step in this case, and the atoms didn't move. And the change in the frequency is, we have a reduction in frequencies here, so okay. In this case, only one step, one cycle of the shaft. So that's about it. So in this way, we have now these files that are the dynamical matrix. We can final SHA, for example, the first one. Here we have the dynamical matrix with all the data that we need for the next calculation.
Remember, these are the auxiliary dynamical matrices.
Yeah.
So far, we didn't calculate the Hessian. So this
No,
is what we did yesterday.
this is just for the we have just now the same as yesterday, calculating the minimum of the free energy. Right now, we need this in order to calculate the rest of the.
But we don't have that.
But
Data, there is no such file like that.
probably you have with a different name the output.
No, yes, the SHA plot data, just like. If you try without Python. Yeah, if you try without Python.
Without Python.
SHA, and try to autocomplete with that.
Because if you have installed it with the pip, you should have it in the bash.
Yeah.
So just by typing this SHA plot data,
The Python is wrong there, so you should include Python.
that should work. It works. Okay. Yeah, this is just for this is exactly what we do yesterday. So it's nothing new here. Just that I'm doing worse. But now we can look for the instabilities. And for that, we can copy again this. So Python again, and put the different libraries. In this case, right now, I'm going to put it all in one step. And the libraries for the NumPy and plotting. So right now, just loading libraries. Setting the temperature, the number of configurations. This is exactly the same as before. This is the output. Yes, this is exactly the same as before. I'm following the ensemble. Yes, this is for the Hessian. So it's correct. It's just the beginning is exactly the same. we're following the same structure of setting the parameters, loading the force calculator, initializing the dynamical matrix, or that is loading in this case. So we can copy of course, in this case, I'm going to put it by hand here. So here it has two parameters. That is, the first one is the dynamical matrix here. And the number of irreducible terms that corresponds to the number of what I'm doing here. The number of files that we have here, in this case SR3. So that means that we have to put it a 3 here. And with that, we load the dynamical matrix into SSCHA. We force positive definited, make the sum rule, copy, paste. Load the previous calculated SSCHA for the final B. In this case, this number of arrays is also 3 for the final dynamical matrix that should be defined in the paper here in the final done. This one here. In this case, if we take a look to the files, are these ones here. So we can copy this and put it in our code here or following the script. Yes?
I got an error, complex wording, casting complex values to real discards.
No, that's fine.
Okay.
Don't worry about that.
Okay.
That's because it has a complex number. Is that from the NumPy the numerical library? So we're here. We load the previous calculated dynamical matrices. Here, we force the positive definite, and I think I did that already. But that should be, yes, I did it already. Here is the loading of the previous calculated. Yes, here. It's final. We set December. So we create this object, December, setting the dynamical matrix that we have loaded at the temperature that we want. So temperature. I think I didn't put the temperature in my script, so temperature, where you have defined the temperature? 0. Yes. So temperature 0. Seriously? We load, we have symmetrize, we load the sub-nebular, we create the symbol, we have to set the supercell, so copy this also. And we have now the symbol.
I think you have a problem there. You didn't
Yes.
close the parentheses.
I didn't close the parentheses, but should be temperature. There is it will give an error because I will put two equals 0, and now just copy and paste from here. It has creating the object with the temperature and setting the supercell, and that's it. Right now we created the assemble object, so the next step is to generate with this we generate the symbols. It's done. It's in memory. Get energy force from the calculator. This what we have done here is created the ensemble, generated the ensemble with 5,000 structures. In this case, we use the Sobol method. That is better because it requires less number of, in principle, sometimes it uses less number of elements in the ensemble. We get the energy forces using the calculator. And in this case, we don't calculate the stress because this calculator we have here cannot calculate the stress. Then, right now, we have an ensemble with the energy forces. So, we can update the weights. And create the dynamical matrix for the Hessian.
So that's the important new
That's the
command that you need to learn here, right?
yes, that's the important command. It's all the theory that you see briefly with that equation to calculate the Hessian. It's focuses in this call, this function call. So it's quite simple to do this free energy Hessian with this code. Just call this calculation. In this case, we are not calculating the fourth component, the fourth elements. So, in fact, we can repeat it with this to true, just to see that we can also calculate with the fourth terms, but it took longer, much longer. Much longer. Much longer. I hope that you're not doing this. Because this part of the calculation, the fourth element, fourth terms, is what takes a lot of time. So if you are able to make the calculation with these terms, better for you. for this, finding if you need to calculate it or not is more or less experience, as I think we commented this morning that just try to calculate for a simple system, smaller system, if you need it, and if you don't need it, better for you, because these calculations take a long time. So now we have here in the thin Hessian calculated that. So we can just save it for the future, like this. We're just saving this Hessian in the format of quantum espresso, and we can get the frequencies from the diagonalization, like this, that we're just using the diagonalizing the Hessian that we have previously calculated to obtain the frequencies here, and we can plot it. I'm lost here. No, here, just print to plot it. Yes, better to do it by better. In Hessian, close here, close here, close here. And we have here plot the different frequencies. And we have here negative numbers. That means that we have imaginary phonons, frequencies, and that means that this system is unstable. And this is really the idea behind this, finding at which temperature we have the imaginary frequencies.
One comment, so you realize that here, for the SHA calculation was done with a small number of configurations, but the Hessian was calculated with a much bigger number of configurations. Okay? So this is what we were saying, that
yes,
maybe more configurations to converge the Hessian than the SHA minimization itself. Okay? So this is something that actually in this example you have it. So this is something to have in mind.
Yes, also why you have to update the weights for this calculation.
Right. Yeah.
Because you have a bigger number.
So this is something important to take into account. Normally, one should check the convergence with the number of configurations of the Hessian itself. So you can calculate it with less or more configurations and see if the Hessian phonon frequencies that you get are converged with the number of configurations. Okay? So the fact that your SHA is converged doesn't mean that your Hessian is converged. Sorry, Theo.
No, it's no problem. So right now, I hope that everybody is following, because right now what we're going to do is using this to get the second order fast transition. And for this, I don't know if following the same thing that I was doing here, or just presenting you with the code, because in this case, we're going to do a loop over different temperatures, doing exactly this thing over different temperatures to try to find the place where there's a transition. For that, we can exit this code that we have done here. You should have not this piece, because this is a file named phase transition in your directory. that has exactly that. As before, we load this calculator, this is a toy model calculator. Everything here is the same. Setting the configuration, everything is the same until we get to here. Here we set saving the lowest Hessian mode, the lowest SSCHA mode. This is just for saving data for the future. Setting the range of temperatures that we are going to do the calculation, and making a loop for the different temperatures, doing exactly what we have done here. Loading dynamical matrix, creating the ensemble, setting the minimization. Here we have all these parameters correctly put, not like before. Enforcing the sum rule, and making the relaxed object. And relaxing. So the code is exactly the same, but over a loop. Yes, saving for the different temperatures here. Free energy Hessian. We don't calculate the fourth component, what is called the E4 component to make it faster. We diagonalize, save the frequencies. In this case, we select only the acoustic modes with this method here. And later we print it. So this is the code. I can just run it. Copy this fuzzy transition into here to work with that here. So here we have all the files that we used previously. So it should do the different cycling for different temperatures. So it's basically the same. The same that we have done previously, but only with different temperatures. If somebody has any problem following this, this will take longer, obviously, because it's calculating for a number of. How to check if? Ah. So we're going to the previous one. We're looking for the instabilities here. And you mean the Hessian if it's converged? I mean, if taking this number of configuration is okay or not?
Basically, you need to recalculate with less configurations
And see
if your phonon frequencies that you get from the free energy Hessian don't depend anymore on the number of configurations.
So it's something that converts with the number of configurations. So choosing, you begin with a low number, you test something bigger. Yes. You see it converges to something, and when it's the difference is slower, little enough, then you are more or less converted. Taking into account that if you don't use Sobol, it takes random number, random configurations to check it. So it's not, there is a little error.
So this is very system dependent. So if the symmetry is high, this number of configurations is normally small, in the order of 100 to 200. If the symmetry is reduced, this number of configurations can be bigger, in the orders of thousands. So this is system dependent. Always symmetry helps us to reduce this number. So that's why we always approaching the phase transition from above is always a good idea, because this calculation will be cheaper, especially if you do ab initio.
There is a rule of thumb that the number of the number of terms that we use for the Hessian is like 10 or 100 times the one that you used previously for the minimization of the free energy. That's not always like that, but yes. So it's finished here. We should have here the Hessian for different temperatures from 100 to 1, from 50 to 300 here. And with this, we can plot you should also have here, no? To plot, let me check, because probably that's one of the exercises I put to second order. We do the calculation. And you can plot this here. Oh, I see. It should be I'm trying to follow.
Is it calculation of the versus temperature file?
Yes, I think just I have to Hessian versus temperature. Of that of food frequency, this was from the previous one. I'm a little lost in these files. So let me check it. If we have here the graph. Oh yes, we have it here, but it's all horrible wrong. Yes, this is horrible wrong. Probably because we have the number of configurations is too small to make a proper calculation.
Is this this result or not?
This is the result that we have obtained right now. So it's I have calculated previously other ones, obtaining more or less the same horrible number with things. We have we need to calculate it with a bigger number of the configuration, number of configurations, because with this low number of 50, we obtain things like this. We need more bigger number of configurations to obtain something like this. In this case, we use 5,000 configurations to calculate this. With much bigger.
Okay, so here in this loop, you are not recalculating with 5,000 configurations after.
That's the thing. We should change the code to calculate with that number of configurations. So let me check it. SHA, fuzzy transition. Let me check. We're here. We begin with 50 configurations here. And we recalculate with 500. It's in the loop.
In the loop, up.
Up.
With up.
More up.
Yeah, you have
Yes.
there with configurations, I think it's 50.
50, yes. So we have to increase the number of configurations for the Hessian.
So this is actually an example why I was telling you. So even if the SHA is converged, the Hessian is not with 50 configurations. So that's why you need to regenerate after the SHA minimization, more configurations, calculate the forces, and calculate the Hessian in that case. So there,
In this,
there where you have ensemble generate configurations, there you are using 50 in this case.
in this case,
So it would be a good idea to use a bigger number there.
we can multiply by 10 or 100
100 is already.
of 10
Or 100.
and try again.
For this code, so if later we face some errors, we can share our errors to get help.
There is on the SHA, on the GitHub, there is for the container of raw SHA code, and there is a discussion, and you can ask questions in the discussion.
Yeah, the best thing is that you use this GitHub. Yeah.
And right now we're recalculating with a bigger number of configurations, and it should be better.
What was the factor that we multiply
Yes.
by 10?
Yes, by 10. In the Hessian, inside of the loop, there is.
No, I just wanted to ask John or anybody if you can explain this a bit more. I don't know if I follow. I mean, I don't know if because we have now a loop in temperatures, we need to increase the configuration.
It's not because of the loop, it's because of if you remember from Rafael's lecture, so well, he didn't give the explicit equation when he was calculating the average of the third order force constant. In the end, we can check the papers. This implies calculating averages of displacement force. And for the SHA minimization, you need displacement and force. So statistically, it's more difficult, let's say. So it makes sense that for the Hessian, you need more configurations because it's a more complex variable, it's a higher order variable. So that's why you need more configurations normally to converge the Hessian.
You should check if the number of configurations that you want yourself is enough. And if that's enough, then you can increase as much as you want.
Here, this is the point where you have to change the number configuration to 10 times bigger. It's the 18th of December for the Hessian. Hessian, no. Is it here? Inside of the loop. Yes. Okay, it's done. So we should have a new output. This is the same one. Where is saving? Minus half. December, that weights, Hessian for different temperatures, getting the acoustic modes, the lower one,
No, going vacation to your parents.
we should have for different temperatures Hessian versus configuration.
Oh,
And
like my mom goes.
an output for a graphical output for this. So
So she goes to vacation. She has to cook all the food what she's going to eat.
this here,
Partially she doesn't.
Hessian,
I mean, he does. No, we don't have a fire.
configuration, Hessian versus configuration, temperatures,
So I have this year, because my sister's wedding was pretty early, I came early.
Hessian versus
I don't know what they're doing. He doesn't want my sister comes to visit us. She cooks. He doesn't want to. He doesn't trust. He really trusts my mother.
Hessian versus.
Well, that ain't he didn't want to eat it. He saw how I made the pizza. Go eggs? No, not eating.
labs.
during COVID, we make narratives and like the at the end. But I invited some Irish friends, and they didn't want to invite it because what I do is you cook first, and you cook like cooking that, so you put another one picture. So you put new one. They don't want to eat that because they are close to each other.
They can touch.
Yeah. And like that, even people functions would be like empty.
Yes, but you also see some cultures also like the oil, they think of this something like I if they are too from here, yes, they use Molina, which is like a process that fruit tastes similar, because it's not another cooker too much time, but why need it inside the soup?
The adventure.
What kind of thing?
No. We drink like usually.
Not tea.
But he loves beers.
Yeah, so it's but in England, they don't. No, I don't also on breakfast. Here, people use breakfast like a shop, like a beer with a roll inside. I know. Oh, the Irish tailor, like a very manly thing, like a beer with a roll.
No,
That, I mean, not try, but maybe also.
yeah, nobody told me.
He also like this, sorry, sombra, Chana, which is like anise, superpower, another superpower, for some reason, kind of portrait.
But that's so morning.
Yeah, like traditionally, but actually common. I mean, less and less, I mean,
Yeah, dying out. Yeah.
this kind of same thing like in Ireland or Scotland, probably. The proteins.
So much drama during the last few days.
Have to put it in the big bag. What is like a brand? So it's hard. It's not like
It is no.
it's not like deal like that.
It is kind of like because it's very hard.
Yes, but it's more like expensive.
It has aroma, but it doesn't have aroma like whiskey.
Not that much.
It couldn't have aroma like liquor.
But brandy is not this type of wine. It's not a moving water from the wine. So
Just distilled.
yeah, so the thing like I know it's brandy was another version that is called. They say that it was invented like from
wine, cheaper to remove the water, and then when rotating the mixer, somebody tried fast moving, so that's why the origin.
I don't know. I think in those times it came
Yeah, I think this is a brand is a kind of version of this thing that they use wine, which you remove.
that's cognac.
Maybe. I don't know.
Cognac, I think, is like a bad wine. That's the only
Yeah, make it strong. Yeah, you know, like, I want to be able to sell that wine.
I mean, much is abomination. It's not compared.
Have you tried? You went? Yeah.
It's very common. It's very common. I have a few friends. Few people say, and the one that I drink,
Yeah, I don't know. China, they drink as much as in Japan. Yeah. That's okay. Yeah, you have to drink with people. Yeah, it's more social. Yeah, in that sense. You have to drink both. Here we want to have dinner and whoever wants can drink and you can now come and it doesn't matter.
there was a bottle in my group when I was a PhD. And he was a funniest guy. Like, he would get 2 beers. They would be starting and he was already drinking. But he was happy. So it was fun. If he was Serbian, I gave him also 2 beers. But he would hang out with him.
Fun like
Yes. But there was a guy. Did you put you were at UAS? Were you at the SSCHA?
yeah, I know, yeah.
Oh my god. He was if he wasn't drugs, then I would have. But he was doing crazy stuff. I cannot like figure out if he's joking.
Okay, but the one
He was making like really weird connections. He was making like connections with casinos on the street with undiscovered superconductors.
maybe he got too crazy. Story lines and bring certain together.
He was like, this was found out here and this is some casino and then we go here. He has a full talk, but you don't know if it's like he's drunk or just accent. He's talking about the you get this, and I'm like, no, don't worry, nobody gets. No, it was, and like the whole talk, there was no point to it.
Yeah,
That was the end of the talk.
it was like a state of the art kind of thing.
I didn't know what he was doing. Did you even try that time to get visa? Yes.
They in Britain they will say like while toilet people are like some sort of
not letting them become. No. Like,
Meaning for the researchers.
yeah, for out of the research for the institute to people that were not there is a 15 days or so. They will work wait, 2 days before, like, so obviously it doesn't matter. Maybe you can, when you apply, I mean,
Insecure.
yeah, it's the more solution. Yeah, I guess.
We wanted to get like cheerful people want to work in Apple, like 200 euros forever. So I'm good.
Yeah, now this has been on the one with the Taiwan,
You mean the semiconductor?
yeah, company going to use saying like they want downgrade the standards they want they always speak the same.
The American part, which is strong arm entire world. It's Taiwan.
How is the China like manipulated Taiwan? It's a big thing in the news and how is in China regarding to Taiwan? Like it's a big thing in the news, like public concern, like so it's very present. Yeah, I know. Yeah. No.
Because
They think they are China.
yeah, people in Taiwan think that
China
the
is a
rest of
province.
China is the province of China. Which dialect do they speak?
Oh,
But it's mutually intelligible, so you get to the Taiwanese person without
Yeah, the one that is open.
yeah,
It's the one
they produce
the only
80%.
it's the only one besides the one in
90% of all high grade.
the only factory besides the one that are inside China. I don't know the new one.
90%. So they have like monopoly on chips. Like high grade chips.
So some of your friends they moved to Taiwan.
yeah.
Okay.
There is an error here.
That you catch.
Yeah, I'm more. Want you to go and Taiwan is the only one that is out.
I think that there is an error in the code that I put it in the file in the paper in the PDF, and it's not reading correctly the output. So probably I have to recheck it because
Yeah, we can fix the PDF
usually when the certain temperatures run to the police, so it's not keeping the data out of the code.
Okay, so anyway, we will fix the PDF.
Something that I just discovered right now, making the calculation, the data doesn't make sense.
How many configuration are you using?
50 for the minimum.
No, but with 50 it's right, it doesn't make sense. So with more than
Yes, but even that they didn't have the output for the correct output for the data.
Okay.
I don't. I have to check it if the PDF is okay or not, because this is the from the web page. And we are, no.
There is one.
No, but this is another thing. Okay. So in the look of the energies, it's
save action. How many?
because it's lower temperatures, higher temperatures. I think.
Anyway, so okay. Anyway, if there is some mistake, we will fix the PDF. So anyway, thank you for the attention. I think we will start again at 2:30 is to correct the hour of the program. So at 2:30 with the lecture, and we have 2 hours of break. So thank you very much for the attention, and we will continue with the lecture of Raffaello.
Oh,